right, let's continue with confidence interval. So the first 2 points we're going to look at is one is point estimate and then interval estimate. So with this one, point estimate is you look at this situation. This time you have a population and you don't know the mean of the population, which is really what usually happens. Okay, so this is the kind of real life application. What you need to do is you can't test the whole population. Again, you have to do some sampling. So let's look at it. If you take a single sample, the sample mean will give you an indication of the value of the population mean mu, which you don't know. Okay, so again, the value of the sample mean can be used to estimate the population mean mu. Since this is a single value estimate, it's called a point estimate of mu. So here we select a random sample of 100 year 12 math students, find that their mean IQ is 108.6, so that sample mean can be an estimate of the population mean mu. Now, as you take a single sample, that value will change from sample to sample. So to use one single value, it's going to be inaccurate or risky. All right, so what is required is an interval that we are reasonably sure contain the value mu. So an interval estimate for the population mean mu is called a confidence interval for mu, and we want that confidence interval to be in the high 90%. Okay, so a visualization of that is, let's say this is the population mean that we want to find out, and as you take many samples, they will spread. In red will be the sample mean, and you can see you have various sample mean, and as you take it will be based on the sample size as well as the number of samples that you are taking, and you will estimate that 95% you're pretty much sure, or 90% depending, you can vary that percentage, that the population mean is within that interval. Okay, so first we have a point estimate, which is this one, then a series of them will give you an interval estimate, and then what we're going to lead to is how confident we are about that interval. So let's go back a bit. We have our let's say we have our distribution. It's a random variable. It's a size n that is pretty large. We're going to look at the sampling distribution, or the sample mean. It's going to be close to a normal distribution, so we have all those respective features. Now, if you standardize that and you're within 2 standard deviations, you put that on the CAS to have 95%. Those values are approximate. Okay. Now in further math, that is rounded off to 2. That is why it's called 2 standard deviation. But actually it's 1.96 and so on. Okay. Now Z is been standardized, so we go back to our original expression in terms of the sample mean, the mean, and its sample standard deviation. And we rearrange that and simplify to make mu the subject. Remember, mu, the mean of the population, is what we're after, and that gives us that the interval for which we have a probability of 95%. So that interval will contain the value of the population mean mu, which is what we want to find out. So from that, we're going to use that lower interval and a higher interval, which is instead of having a probability notation, we're going to call that 95% confidence interval from starting from this boundary up to that one. That is our sample, the value of the sample mean. Sigma is the value of the population standard deviation, and n is going to be the size of the sample for which we calculate the sample mean. Alright, example, really direct application. Pause the video, probably write out what variables you know. Now let's move on. We know the sample mean, which is what it is to what we have. Okay, we know n, the standard deviation is 15. You substitute that into your confidence, 95% confidence interval, and that gives you those values. Therefore, based on a sample of size 100, a sample estimate of 108.6, we have an approximate 95% confidence interval for the population mean to be within that interval. Okay, so going back to this, basically what we do is we calculate, we have the sample mean, we determine the confidence interval. 95%, it means that new value has to be somewhere in between. Alright, let's move back forward. So we've done that. You can also do that on a calculator. So following those instructions with those menus, you enter those values, okay, and you get your lower boundary and upper boundary, we get the similar answer. Notice ME, it's what we call the margin of error, and we're going to use that pretty soon. So you can determine that that information from the same sequence of instruction with the same function. Okay, margin of error. So we can do that on the Gauss calculator. So for 95% confidence interval, the margin of error is given by this value. Okay, it's 1.96 times sigma over root n, and it's coming from, see that that formula, the sample mean plus and minus, that amount is your margin of error. If we rearrange that and simplify to make n the subject, we can determine the sample size required to get a 95% confidence interval. Alright, application. So we want to find the sample size. The margin of error is 1.5 or less. It's a 95% confidence interval, and we have sigma. Substitute the values, we get that value. We round it up to 385 students, and that's the minimum required for the sample size. Alright, now let's say we want to adjust. So we know that for 95%, which is what we have here. Okay, for 99%, it will be given by that value, and in the next slide I'm going to show you how to calculate this value, 1.96 and 2.58. What we do is, within the interval, we instead of having that value, we have a factor k, and to determine that factor k, what we need to do is we do that probability needs to be between that interval and the percentage confidence that C value is that is what we need to determine. All right, let's continue. I will come back to how to calculate that K value, as we haven't covered the inverse normal function for a standardized variable. Okay. All right, so here we have three respective confidence interval. We know the sample size, we want the mean to be that amount, and we have the standard deviation. We got from the 95%, we got that interval. For 90%, you will have a value of 1.65. You substitute those values and you get the interval. For 95%, we use the 2.58. You substitute the values and you get that interval. So as you increase your percentage confidence, your interval will be wider, obviously. Okay, so this is what you aiming for. Standard is 95, but it could be any value. Again, later on you will use a function called inv normal to determine the boundary of a probability. And that's it for this session. See you later.